Welcome all to session 5 of this lecture on architecture and programming models for GPUs and coprocessors. We are still talking about the performance of computer programs. While we, during the last sessions, had a very practical view on performance, we'll now take a step back and have a more theoretical view that will help us to better assess the complexity of parallel algorithms. We have learned about the relevance of concurrency and of parallelism because vendors tend to stuff more and more circuitry into their processors that has to be programmed in a parallel fashion. We already learned about a number of methods and tools that can be used to parallelize our code, and before we do that, we should take a step back and we should actually learn about the parallelization potential that computer programs and that algorithms expose. And the instruments that we will use for that for the time being will be of a theoretical nature. And one of those instruments is the so-called Amdahl's law. And Gene Amdahl, he also was an entrepreneur, and he was with IBM, where he worked on the mainframe computers. In contrast to Moore's law, Amdahl's law is not a prediction, but Amdahl's law allows us to make a prediction. For that, we have to make some simplifying assumptions. So far we learned that computer programs can be parallel or they can be sequential. And in general, computer programs have parts that run in parallel, and then there are other parts that just run sequential. Like, for example, when our computer program loads a file, so that very task of loading that file is usually a sequential thing. Then there are other parts where we have maybe we're loading that file, and then we're using that file as a starting condition for a computer simulation, and then we run that simulation, and that simulation runs in parallel, and those parts would be parallelizable. So our computer programs, we in general assume that there are sequential parts and that there are parallel parts, and those parallel parts, this is what we learned, usually manifest as either programming language statements, like C++ statements, and then they are wrapped in a parallel for loop or in a thread callback. And we also learned that there is instruction level parallelism, where the CPU schedules instructions in parallel. And from now on, we're just assuming that there are parallel parts in the program, and we don't care so much how this parallelism is exposed, if those are statements or if this is instruction level parallelism. But what we are able to do is we're able to exactly identify which parts of the program are parallel and which parts are sequential. Like, we're able to annotate our program and say those parts can run in parallel and those parts are sequential. And therefore, we can also name the exact ratio of parts of our program that are parallel and of parts that are sequential. And therefore, we can express it as a percentage or a value in 0 and 1. No? So when we define that the parallel part of our program is capital P, and therefore the sequential part is 1 minus capital P. And then we define the speedup, and we define the speedup for only the parallel part of the program. This S parallel here, S subscript par. And the parallel speedup, or the speedup of only the parallel part of the program, is defined as the execution time of just that part, like of only the parallel part P, when being executed on a single processor, and that we call T of 1. And the parallel speedup is defined as T of 1 over the execution time of the parallel part being run on n cores. And with that, we can define the maximum speedup for the whole program. And the maximum speedup for the whole program is just 1 over 1 minus P plus P over the P speedup for the parallel part of the program. And this is just Amdahl's law. And Amdahl's law, so the the equation here gives us a theoretical upper bound that that allows us to quantify how much the program execution can be accelerated in the best case. As this is a theoretical upper bound, this is something that our program in practice will never achieve. So there's another important observation, and this is that the execution time of a program when being run on n processors is not just the mere time it takes for the processor to execute the instructions, but there's actually more to it. Like when we specify this TFN, the execution time of a program on n parallel processors, what this implies is we have the actual computation time, so the time it takes to execute the actual instructions. And then we also have wait time, and then we have time that is devoted to communication overhead. And the sum of that makes up the execution time on the parallel execution time of our program when executed on n processors. And this is obviously something that you don't have when you run the program on only one processor. Like when you don't have to synchronize with other processors, then you don't have to wait for other processors, and you also don't have any communication overhead. And here's a small example how Amdahl's law can be applied in practice. We're having a sequential program, and we analyzed that program, and then we made an estimate about what the parallel parts of the program are, and we are able to quantify that. And we identified that about 80% of the program can run in parallel. And we also made an assessment of the speedup of that parallel part, and we estimate that the maximum speedup that we can achieve for that parallel part on a multi-core processor is 4x. So, and then we, with that information, like we know our capital P, which is 80%, 0.8, and we also know as par, because we know that 80% of our program will see a speedup of 4x, and that 4x is just our speedup for the parallel part of the program. And with that, we can fill in all the variables in the Amdahl's law, and that gives us that the speedup for the whole program is 2.5. And then we make another estimate where we want to make an assessment, or where we want to make a prediction how fast our program would actually run on a supercomputer. And there we estimate that the speedup for the parallel part of the program would be 200. And then we again compute the maximum speedup for the whole program. And some people might find this a bit disappointing, because it's actually, like, in absolutes, it doesn't feel much faster than the speedup that we achieved on the multi-core processor, even though the parallel parts of the program scale so well, so to say. Yeah, this is what the example aims to illustrate, that even when the parallel part of the program, so that fraction that can be run in parallel, is relatively high, the absolute speedup that we can achieve is really relatively small. Yeah, and like Amdahl's law is really a theoretical upper bound. So in reality, we will actually never achieve this. I actually plotted the result for Amdahl's law, for the Amdahl's law formula, given different values for S par and for capital P, so for the parallel fraction of the program. And you can already see that if the parallel fraction of the program isn't relatively high, then a parallel program will generally not scale very well. That is, even if the speedup for the parallel part is very high, we still see that the whole program, that the speedup for the whole program will be relatively low. So apart from Amdahl's law, there are also a bunch of other ratios that we should discuss. One of those ratios is the efficiency of a parallel program that is executed on n processors, or in short, the parallel efficiency. And the parallel efficiency is just defined as S par, so the speed up we can achieve for the parallel part of the program over n, which is the number of processors. So while Amdahl's law allowed us to assess the parallelization potential of the whole program, efficiency states the relationship between the expected speedup of the parallel part versus the resource usage that is required. And ideally, but this is also something that we'll never achieve in practice, therefore S par would just be n, and then the efficiency would be 1. Like basically this ratio tells us how much speed up, how much parallel speed up do we see in relation to the number of processes that we devote to the parallelization. Another ratio that is of importance to us is the costs of a parallel program. And the costs of a parallel program are defined as the product of the resource usage n, that is the number of processors that are devoted to the execution of the parallel program, times the execution time of the program on n processors. It's kind of obvious that the costs are always greater or equal the sequential complexity. Like we learned earlier that the execution time on a single processor, TF1, is always smaller or equal to the execution time on n processors because there is additional time for communication overhead and for waiting. And from that, it directly follows that the costs of a parallel program are always greater or equal the sequential complexity, and ideally they would be equal. And when the costs are equal to the sequential complexity of the best known sequential program, then we say that our parallel algorithm or our parallel program is cost optimal. Our cost optimality is an important measure because this is what we actually strive for. Like when we design a parallel algorithm or a parallel program, what we're after is what the approach should be is we pick out the fastest sequential algorithm that we know, and then we try to find a parallel algorithm that has the same cost as the sequential complexity of the sequential algorithm. And cost optimality is a theoretical and idealized measure, so we will never actually reach cost optimality in reality because there is additional time for waiting and for communication that just doesn't occur in the sequential case. But still, this notion of cost optimality is a very important one. Like putting the complexity of our parallel algorithm into relation with regards to the best known sequential algorithm is important because we don't want to perform more work than this sequential algorithm, and we don't want to perform more work for various reasons. Like one reason being the throughput argument that we discussed in one of the first lectures, when I brought the aviation example with the Concorde and the Boeing. When we optimize for throughput, we also want to keep the cost down, and we don't want to do more actual work, even if when the work is performed in parallel, we're faster. This is an argument that is important, for instance, when it comes to energy consumption, but fundamentally this is a scalability issue. Like an algorithm that will perform more work than the sequential algorithm will in the end not scale, because in the end it will, even when neglecting the whole throughput and energy consumption argument, which is an important one, in the end an algorithm that will do more work will be dominated by other effects than just the mere computation that is associated with the work, because with the additional work that the algorithm has to do, we also have communication overhead, and we also have wait times that go up. And that overhead, in the end, will cause our algorithms to not scale very well. So we're always after algorithms that optimize for cost. And equipped with this knowledge, I want to introduce a machine model that allows us to analyze the complexity of a parallel algorithm. And for that, we will not only take the asymptotic runtime into account, but also the asymptotic resource utilization, as was, for instance, expressed by the two ratios, by the parallel efficiency and by the cost. I want to note that such a discussion, we can really only scratch the surface here, as such a discussion would be the topic of a parallel algorithms class. This is not a parallel algorithms class, so we'll just try to get a basic understanding so that we later can analyze the parallel algorithms during the course of the lecture that are of importance to us. But a very thorough discussion is definitely out of the scope for this lecture. So with this knowledge, let me introduce the parallel random access machine, which is a machine model for parallel algorithms. And this machine assumes that we have an arbitrary number of processors and that we have an unlimited amount of shared memory. That memory is shared by the processors, and we also assume, as this is an idealized model, that each memory access requires exactly one unit of time. And with the PRAM model, what is also the case is that instructions are executed synchronously. We will call that lockstep execution. And the programming model requires us to write parallel functions that run on P processors. And when we write those functions, we can, inside that function, access the current processor index. Now, the model is very much idealized and simplified, but there's one thing that we have to take care of, and that is the way that memory is accessed when multiple processors try to simultaneously access the memory. We in general assume that simultaneous access is not possible, and instead there are three different types of memory accesses that the machine model can implement. And depending on the machine model, we potentially arrive at different algorithms. And the simplest PRAM model with respect to memory accesses is the EREW machine model. And the EREW machine model only allows for exclusive reads and for exclusive writes. So the programmer has to make sure that memory addresses that are accessed by a single processor aren't accessed by any other processor, be it read or write accesses. So you will sometimes hear me say this is the least restrictive PRAM machine model, and which might be a bit confusing at first, but what that means, this is the least restrictive model when it comes to implementation, like when it comes to the implementation of this theoretical machine. Like, of course, there are no implementations out there that implement the PRAM model, but from a vendor's perspective, the least restrictive model is the EREW machine model. So the next simpler model is the CREW model, and the CREW model actually allows for concurrent reads. And our writes are still exclusive, so the programmer has to make sure that processors write to an exclusive memory address. And then there's the CRCW machine model, where processors are allowed to read from and to write to any address simultaneously. Like this model, I mean, as you can imagine, a implementation of this machine model would, like, under the hoods, have to perform synchronization. Like, this is a model where the programmer really doesn't have to take care of synchronization when it comes to memory accesses, and therefore the processor would have to do that. So that would see the processor enter a critical section or something like that whenever the programmer performs a memory access. So this is a very restrictive model in that if there were such a model, it would probably be a very slow implementation. So, I mean, this is kind of obvious. If you have an EREW PRAM algorithm, that algorithm will only perform exclusive memory accesses, and it's guaranteed that no other memory cells are accessed than the memory cells, the memory addresses that are devoted to that processor. And with that, that algorithm would of course also be runnable on a CREW PRAM and on a CRCW PRAM. And likewise, a CREW algorithm would also be runnable on a CRCW PRAM, but not the other way around. Like when you have a CRCW algorithm, you cannot execute it on one of the simpler PRAM models. It should be noted that CRCW PRAMs are a bit more complicated than what I'm suggesting here. In particular, there are different CRCW PRAM models with regards to the order that write accesses are performed in, like when there is a collision and then when there are simultaneous accesses. Then there are different models that specify the order in which the processes write, because this is important in order to assess the program's correctness. This is, however, an advanced topic, and we will not discuss it in this lecture. And let us have a look at an example, and the example is the Zaxby program again. And what I'm presenting you here is an EREW PRAM algorithm that can run on P processors. And in order to run the program on P processors, I'm writing this parallel function here. And like I said, in the parallel function, I have the processor ID available, this ID P here. And I define, for the sake of this example, that the processor IDs are within 0 to P minus 1. Like they're integers, 0, 1, 2, up to P minus 1. Then I'm also defining the input, like the input I'm processing is of length n. And I also make the assumption that n is always greater or equal P minus 1. And then I'm also making an assumption that all the array indices that you will see here are 0 based. Those are assumptions that I'm making for the sake of the example, so they are not general assumptions, but they are only valid for this example. And let us have a look how to implement this algorithm for the EREW PRAM. And you will find things very familiar. Like the range computation I'm doing here is the exact same range computation I also had to do in the thread callback example that we discussed earlier, and also in the distributed memory MPI example that we saw. So I'm first computing based on the current ID of the processor. So of my processor ID, I'm using my processor ID to compute the range that my processor is responsible for. Like I'm computing the first item and I'm computing the last item, and I'm making sure that I'm not reading or writing beyond the end of the data array, which would, in our case, I mean, it would be kind of okay to simplify things a bit here, because this is a theoretical model. But nevertheless, so I'm doing those range computations. And then I'm again performing the Zaxby for loop, and similar to the examples that we saw before, I'm performing the Zaxby for loop for only the range that I'm responsible for. So for roughly n over p data items. So why is this an EREW PRAM algorithm? This is an EREW PRAM algorithm because each processor will only read from or modify exclusive memory addresses. So this I here is really only ever accessed by a single processor. And because of that, because my algorithm makes this guarantee, this algorithm is executable on an EREW PRAM. Like if this was not the case, if I were to perform simultaneous accesses to the same memory address from different processors, then this would not be a valid EREW PRAM algorithm. But because I'm making this guarantee, it is. Let us have a look at the runtime complexity of this algorithm. And the first three operations that I'm performing are constant time operations, but they are performed by P processors, right? So the complexity here with respect to runtime, because I'm assuming that all processes can operate simultaneously. The processors are operating simultaneously and in lockstep, and because of that assumption, the running time for the respective operations here is constant, but it is performed by P processors at the same time. So these three assignments obviously are constant time operations, and this is followed by this for loop here, and the for loop here runs over roughly n over p, and therefore the asymptotic complexity of that is n over p, right? And that gives me the execution time of this parallel function, of this parallel algorithm on p processors, and the asymptotic execution time is just O of n over p. I mean, this was kind of expected, right? Because we know the runtime of the sequential algorithm, which just happens to be O of n, right? Because it's just an iteration over an array of size n. And now what we also can see here is we can assess the costs of this algorithm. Like we see that the costs of these algorithms are roughly the same as the sequential complexity, right? As we're having our runtime t of n, that is O of n over p, and when we multiply that by the number of processors, we again arrive at O of n. So, and for this very simple algorithm here, we have a cost optimal algorithm, in a sense that if there were no waiting times and no communication overhead, we would arrive at the very same costs that we have for the sequential algorithm. And I mean, that's obviously a very bold statement that I make there, and it is actually only valid because of the assumption that with the PRAM model, processors are retiring instructions in lockstep. And on a real machine where this is not the case, we would obviously, even in this very simple, in this embarrassingly parallel example, we would see wait times, and therefore the algorithm is cost optimal, but only in theory and only on this very idealized machine model. So now I want to introduce a simplification to the PRAM model, and that simplification is commonly referred to as the Worktime Paradigm. We will later learn why it is called that, but let me quickly explain what the simplification will be. The simplification will be that we from now on will try to not express our algorithms in terms of P, but in terms of an infinite number of processors. Like with the PRAM model, we are always assuming that there is an arbitrary number of P processors, but there's a definitive number of P processors. And with the model that I'm introducing now, which is basically an extension to the PRAM model, we'll make the assumption that there is an infinite number of processors. And this will simplify our algorithm a lot, because in the end, we don't have to take care of ranges anymore. And the extension that I'm presenting here is pretty much analogous to the two multi-threading programming models that I introduced earlier. The one multi-threading programming model where we used thread callbacks and maintained threads ourselves, and the other programming model where we had a parallel for loop and we weren't aware of how many threads there are. Like there is a thread pool or something, and there is a mechanism, the parallel for mechanism, that will ensure that there is enough parallelism and that there are always threads that will process the work. But we don't have, in particular, design our algorithms around the knowledge how many processors there are, and in particular, we don't have to take care of a subdivision with respect to that number of processors, and by that, we can basically do away with those ranges that I computed earlier, like the first and last range, and that significantly simplifies the algorithm, and that also makes it easier for us to reason about the algorithm. And the work-time paradigm, or the work-time formulation, achieves that by basically separating the resource usage from the runtime. And what we end up with is separate notions of complexity for both the work that the algorithm performs and for the time that the infinite amount of processors require to execute the algorithm. And this is what we were initially after. Like when we discussed parallel efficiency and when we discussed costs, we were after a model for our analysis that allows us to both analyze and assess the time complexity of our algorithm. So what is the runtime of our algorithm? And judge that in relation to the work that is performed. And therefore, we define two types of complexity. And on the one hand, we have work complexity, which is just a total number of parallel operations that the algorithm executes. And then we have time complexity, which is the number of single steps executed by the algorithm, also called the step complexity, S of n. So we, on the one hand, have a complexity with regards to the actual work, and then we have complexity with regards to the number of time steps that are performed, assuming that some of the work can be performed in parallel. So, and per definition, we have that the total work complexity is the sum of the individual work complexities of each time step. This variable w subscript I is just the number of parallel operations per time step I. And with that, we have the general procedure when we design a parallel algorithm of first finding the most favorable sequential algorithm, and then finding a parallel algorithm that will try to retain the work complexity of the sequential algorithm, that will do the same work but minimizes the time complexity. And this is the same thing that we discussed when we talked about costs and when we talked about parallel efficiency. And we're now incorporating that into the machine model. So we have a machine model that allows us to, across all processors, perform the same work but in less time. And with the work time approach, we formulate our algorithms differently than with the PRAM machine model. In particular, we now don't define parallel functions anymore, but we instead define sequential functions, and those sequential functions can make use of parallel for loops, like this language construct here, basically, like this construct that is provided by the machine model will see those n items being processed in parallel. Note that the same assumptions about memory accesses, about EREW, CREW, and so forth, still remain valid for this machine model. So we still have to take care of this, and all the other assumptions that we were making for the PRAM machine model still stay valid. Only the way that we describe the algorithm in terms of how many processors are used, like in terms of the resource usage, is now different. And we will from now on prefer this formulation to the PRAM formulation. And in the following, I will also show you a real quick why this is valid, why we even can express every parallel algorithm that can run on a PRAM, why we can express it with the work time approach. So, and in order to show the validity of this approach, what we have to show is that if we were to make that formulation with respect to work and with respect to time, and if we were to take that algorithm, that formulation, and would reformulate it equivalently for a PRAM, that there would be an upper bound for the number of parallel operations that the PRAM algorithm would perform. And I'm now showing you that this here is an upper bound for the number of parallel operations that a PRAM would perform for a for an equivalent work time formulation algorithm. So there's the thing that we already know about the PRAM model and about the work time formulation, and that is the number of parallel steps that a PRAM would take to execute a single time step from the work time formulation. Like given a single parallel time step in the work time formulation, we know that this could be equivalently formulated on a PRAM model, but would take W of I over N, so the parallel operations performed in that single time step over P operations, but that rounded up. And with that, we already know how many PRAM time steps are required for a single time step in the work time paradigm. And from there it becomes simple, because for the whole program we just have to consider the sum, and in particular the sum over all time steps that the work time formulation takes, and therefore we only have to show that this here is an upper bound for that. So, and this is easy to show, like this here is just that, and you can also see that this here is an upper bound for that, right? And you can also see that this is an upper bound for that. Yeah, I'm basically just replacing the sum over the time steps with a multiplication. So this is kind of guaranteed that this is an upper bound for that. And this here is just that. And that shows what we wanted to show. And if you're at odds with my handwriting, here's also a single slide showing the whole thing. And the whole thing is called Brans Theorem, and it's actually a very powerful theorem, because it tells us there are equivalent formulations, PRAM formulations for every work time program, and that there is also an upper bound for the number of operations that a equivalent PRAM formulation would require. And this is a very, very powerful full theorem, because it allows us to express every PRAM algorithm with respect to the work time formulation. And as I said earlier, we will make use of this, and we will from now on, when we later consider computer graphics algorithms, when we consider other algorithms and want to formally analyze those algorithms, we will use the work time formulation for that. Yeah, and let us strengthen our intuition here with an example, and let us pick an example that's a bit more complex than the Zaxp example that we've been considering all the time. And the example that we're considering is called reduction. And reduction, in the simplest form, really just means that we compute the sum over the elements of an array. And there's actually a very simple algorithm that we can use to perform reduction, and it's a sequential algorithm, and it just goes as follows. We initialize a variable, the result variable for that matter, with the first element of the array, and then we add the second element of the array, and we set the result variable to the sum, and then we add the third element of the array to the result variable, and then we add the fourth variable and the fifth and so forth. And I mean, I guess you'll believe me that in the end we performed, in this case where we have 8 array entries, that we performed 7 additions. And you can also believe me that the sum is 26. So here is a pseudocode formulation for that algorithm, where we initialize our result variable, and then we sequentially just add the next array element to the result, and the complexity of that is obviously over n. So this is like a very, very simple algorithm. So let us consider how one would implement that in parallel. Like how would we parallelize this summation? And the idea is to use a binary tree for that. Well, like reduction really means we're performing binary operations. As a matter of fact, reduction in general doesn't require us to perform additions, but reduction is an algorithm that can be used for any pairwise binary operations that are associative. But regardless of that, the idea is that we perform pairwise binary operations in parallel, and thus reduce the number of times of steps that we take, the number of parallel steps, to log n. And so let us just return to our virtual whiteboard to see that in action. And we have our array again. And now, instead of performing a sequential sum, we're instead having each of P processors perform pairwise individual sums. Like processor number 1 would perform a sum over the first 2 elements, and processor number 2 would perform the sum over the third and fourth element. Processor 3 would sum up the elements 5 and 6, and processor number 4 would perform the sum over the 7th and 8th element. And all that would happen in the first time step, and that would give us in the first time step 1, 2, 3, 4 parallel operations, which we in our framework would call Wi, or in this case W1. So and then we would write the results of those additions and write them into a temporary array. And then we would again perform parallel additions. And in the second time step, we would perform 2 operations. And we can also see that processor 1 performs the addition of the first 2 elements in the temporary array. That is the sum over the first 4 elements in the original array. And processor number 2 performs the sum for the third and fourth element. And processor number 3 and processor number 4 idle. And so that way we would have 2 parallel operations in the second time step. So our W2 is just 2. And then in the third time step, as I already said, this is an algorithm that performs log n time steps, and n is 8, so we're performing 3 time steps here. And in the third time steps, we're only performing 1 single parallel operation, and processor 1 performs that addition, and the other processors idle. And then in the end, we arrive at the same result. We arrived at with the sequential algorithm. And let us analyze the complexity here. Like the work complexity is just the sum over all time steps, and the time steps I already told you is log n, and in our case happens to be 3. So the sum over the 3 time steps, and which is just 4 parallel operations in the first time step, 2 parallel operations in the second time step, 1 parallel operation in the third time step, which gives us 7. So, and those 7 additions just happen to be the same 7 additions, or not the exact same additions, but the same number, 7, of additions that we also performed in the sequential case. And because of that, the algorithm has the same work complexity as the best sequential algorithm that we know. So, and let's have a look at a PRAM formulation of this algorithm. And before we do so, we make some simplifying assumptions, basically so that I can fit this algorithm on a single slide. And the simplifying assumption is that n is power of 2. And we also assume that we have P processors, and the number of processors is just n. Those are simplifying assumptions, but they are helpful because that way I have to care way less about ranges and range checks than as if I would formulate that algorithm in a more general way. And we're also assuming that we have access to the processor index P, and the processor ID is now 1 based. So the processor ID is either one of 1, 2, 3, 4 up to P. So here's our function reduce PRAM, And the very first thing that I do, I take the input array and for convenience, just copy it to a temporary array. Yeah, and I basically do this. So I cannot in the following just overwrite the input array. So in order to have like some scratch memory that I can perform the operations in, I will just use a temporary array. And we already discussed we're basically traversing a tree, like we're basically traversing this binary tree here, and we know that we will perform log n operations, which just happens to be the height of that very tree. So we're just performing those log n operations, and whenever I perform that operations, one of those operations, I just halve the number of processors that are responsible for the computations, or that participate in the computations. And I basically do this by having a branch, having an if condition, and that if condition basically tells me if the processor currently participates in the computation or if it doesn't. And if it doesn't, like here's no else branch, so the processors that don't participate basically do nothing. And with every time step that I take, with every step through that tree, effectively the number of processors participating halves. And then I perform this operation where I sum the two elements that the processor is responsible for, and I store the results in the respective element of the input array, of the temporary array. And then eventually, finally, when I have traversed that whole tree and performed my log n operations, I know that like what I'm doing here is I'm moving the result further and further to the left. And then in the end, I know that the result will just be the temporary array entry to the very left, so where the index is 1. And then I just assign the leftmost element to the variable that I'll eventually return. Few remarks. So this algorithm can be executed on an EREW PRAM. The complexity on the PRAM is log n. So the asymptotic number of parallel steps that our algorithm takes is dominated by this for loop, right? And thus we use log n operations. And yeah, what we also can see is that the PRAM formulation requires us to express this algorithm with respect to P processors. And if we were to reformulate this algorithm with respect to the Worktime Paradigm, we'll, instead of writing a parallel function, we would write a sequential function, like this one here, and we're now calling it reduce work time. And this function first performs, like before, the copy operation was a single parallel operation, like performed by all processors, and now instead we have to, inside the sequential function, we use a parallel for construct that will just copy in parallel all the input items to the temporary array. And then what we're basically doing is we're pulling the iteration over the log n time steps. We're pulling it out, like the parallelization now actually happens inside that iteration over the log n time steps, right? Like with the PRAM model, you'd have an implicit parallel loop or a parallel construct because the function itself is parallel. And now we're moving the parallelism to the inside of that parallel loop over all the time step. And then inside that loop over all the time steps, we perform log n parallel executions of that summation, where we, like in the PRAM case, have the number of participating processors during each iteration. Yeah, and as you can see here, like in the PRAM case, I implicitly had access to this number, to this ID, to this processor ID P, and instead, in the work and time paradigm case, I have to construct that number p myself, and I construct that basically just as the for loop index. So, and then in the end, I mean, this algorithm performs the exact same calculations as the PRAM algorithm does, and then in the end, the result is again in the leftmost array element, and we can just return it from the function. Let us now analyze the complexity of this work time program. Like this very first loop here performs n parallel operations, and as they are parallel operations that all happen in a single time step, we need a single unit of time to perform this operation. And this is followed by our for loop, the for loop that dominates the algorithm, and the for loop is executed log n times, and each of those log n operations we perform a parallel operation. So once again, each of the parallel operations can be performed in a single time step. So that means that the for loop takes log n times 1 units of time. And then in the end, we have our assignment, which is really just another unit of time. And that means that our parallel function with respect to time has complexity O of log n. The work complexity is determined differently. The work complexity is determined as follows. In the first parallel for loop, that parallel for loop takes 1 unit of time, but we perform n operations. Then we have our dominating for loop that is executed log n times, and during each of those operations, each time we execute this inner for loop, we have the number of processors that participate, and thus we also have the number of operations that are performed in the for loop. This is for granted, this is a bit sloppy to write it this way, but effectively what happens is that the logarithm and the halving of those operations per for loop execution basically cancel, so that they together just form n iterations, right? Like when you do the math, you will find out that over those log n time steps, and when you each of the time just halve the number of operations that is performed, you will just find. So apart from the writing here that is a bit sloppy, you will find that overall you will perform n operations. And then in the end we have another operation, and that way we find out that our for loop has a work complexity of n. So this is the basic procedure that we perform whenever we analyze a parallel algorithm. So we first of all we determine the number of time steps that is performed by our algorithm, and then we count for each time step how many parallel operations are performed in each time step, and then we compute the sum of that, and that gives us the work complexity. And like I said, what we're after algorithms where the work complexity, where we perform the very same work that the sequential algorithm would perform. And in here, this is the case. So a few remarks about this algorithm are in order. Like, we already analyzed the work and time complexity, and I think that this concept is fairly well understood now. And I already said that the algorithm reduced work time computes the result on an EREW PRAM with P processors. And there's something noteworthy about this. Like, when you have a look at this assignment, like this is the assignment from the inner loop, you see that there are potential collisions. Like when you write it down, you will see that sometimes you have processors that would assign their temporary array P and would access memory addresses that other processors use. And there's a certain peculiarity to the PRAM and to the work time execution model, and that is lockstep execution. And lockstep execution guarantees that those axes, like the write axis to the temporary array here, performed by, say, processor number 1, and the read axis to the temporary array performed by, say, processor number 2 or processor number 3, never happen simultaneously, because the processors will execute all statements in lockstep, right? Like, all processors will first perform the read operation, and they will do this simultaneously, so there will be no chance that there is a collision. And then all processors will perform this read operation simultaneously. Again, no chance for a collision. Then the processors will perform the addition. And then the processors will write their results, and everything happens in lockstep to the PIV address in memory. And only for those reasons, this algorithm is an EREW algorithm. And I mean, when I'm asking the question about the practicality of this, this is of course not very practical. Like, this is maybe practical when you're in a SIMD programming model, but as soon as you're working with threads and on a multiprocessor, multi-core architecture, then this is not very practical, and you will want to make sure that those collisions don't happen, right? And nevertheless, this algorithm is a valid EREW algorithm, so the algorithm makes a guarantee that there will be no simultaneous accesses to the same array elements. And therefore, we can use an exclusive memory access model. And that should also illustrate how practical those models are. Like, those models allow for a certain reasoning, but when you were to implement this algorithm on a real-world architecture, you would certainly have to take care of that there are no collisions. Yeah, and let us just have a closer look at this. What is happening here is that basically, like, when we just unroll in our mind the operations that happen here, is that we have processor number 1, and processor number 1 will write to this memory item 1 here, and processor number 1 therefore will use the data items at address 1 and at address 2. And processor number 2 will sum up the values from 3 and 4 and will write the result to memory address 2. So, and at this time, there's not a problem here yet, because there are no collisions. But as soon as we have a look at what processor 3 does, processor 3 actually writes to the temporary array here at address number 3. And when we're in a lockstep architecture, then this is no problem. But when we're in a multi-threading architecture, we have a potential data race, because we don't know yet if this write access here has happened before or after this read access. So we'll get a data race, right? So there are a number of things that we can do about this. So the obvious thing is that we just introduce a critical section, which we don't want to do, because this basically serializes our program. So that's something that we really want to avoid. And another thing that comes to mind is that we just use more than one temporary array, like that we store the intermediate result into another temporary array, and thus basically using more memory. Like, this might be an option, but it's something that we want to avoid. So the question is really, can we adapt the algorithm in a way so that it can be executed on a machine with multi-threading, so that it still stays the same valid EREW PRAM algorithm without serializing parts of the algorithm, so without introducing critical sections, or by still having the algorithm being an EREW algorithm, but relaxing the assumption that the model uses lockstep. And by that, it would become much more practical for us than the EREW PRAM or Worktime algorithm. And for that, we should have a look at we should come up with a better way to perform the memory accesses, and this would go as follows. So let us just discuss the memory access patterns of the algorithm that I showed you so far. What I'm depicting here is this temporary array T. So those aren't three different arrays, but they're actually always the same array. And I'm just illustrating how we're updating that array over time. And with our algorithm, the memory access patterns go something like this. Like we compute the sums pairwise for those 8 elements. And then we store the result in the same temporary array that we also draw the operands from. And we store the result consecutively, like we store the result of the first addition in array entry number 1, and the result of the second addition in array entry number 2, and so forth. And this is actually where our race conditions can happen if we were to be in a multi-threading context, right? Because in the multi-threading context, we have we have the read operation, and then we have the summation that happens over here, and then we have the write operation. And we are when we are in a lockstep execution model, and everything is fine. But as soon as we're in a model where lockstep isn't guaranteed, we have those potential race conditions because between those three operations, between the read axis, between the write axis, and between the addition. And as you already can see, we have simultaneous reads from different processors to the same memory addresses that are also written to. Like for example, this memory address 3 here is being read from, and at the same time, another processor than processor number 2 actually writes to this address, like potentially writes to this address when we're not performing lockstep. And the same thing happens down the hierarchy until we have reduced the array. And there's a very simple memory access pattern that we can use to resolve those potential data races, and that goes as follows. We just store the result of the addition, but when we store, then for the write axis, we use a stride to access the array that is always twice the stride that we used before. Like we start with the stride that is just the distance for this operation. We have two processors. We have one processor that is responsible for 2 items, and that defines our initial stride, which is 2. And then when we perform write accesses, then we just write our result in to the memory address that is the same memory address of the processor left from us, so to say. So with an index 1 lower than our index, but with a stride of 2. So we take the memory address and then we add the stride. And when the memory address of our predecessor would be 1, our memory address would be 3. And we perform this on and on and on. And that way you can already see that there can be no potential data races, because whenever we access a data item, we're guaranteed to perform those accesses exclusively. And when we write something, we are also writing exclusively. And I mean, we're still potentially writing to memory addresses that another processor potentially later reads from. But this isn't a problem, because those loop iterations are obviously performed in lockstep. Like the loop iterations are inherently synchronized, because during each loop iteration we use a separate parallel for loop. This effectively synchronizes each iteration. And then the next iteration we double the stride again, which in this example gives us a stride of 4. And by that we can guarantee that there are no collisions regarding the memory accesses. We retain the same number of additions, so the work stays the same. We also don't need extra memory. Like we still have the single temporary array of size n. And now with a slightly adapted memory access pattern, we can actually guarantee that there are no data races, even if the underlying machine model wouldn't make the assumption that execution is performed in Lux. So this colorful illustration shows the very same thing, but with regards to processor assignments, like when you're in a PRAM model. And what you basically have to do is you have to double the distance each time you go to the next iteration when you iterate over that binary tree. So with this simple adjustment, we can make the algorithm reduce work time and also the algorithm reduce PRAM. We can adapt it so that it can be executed on a multi-threading architecture. Yeah? Like the only thing that I really do is I adapt those indices a bit so that they actually use a stride that doubles with each iteration. I mean, what this illustrates is that those models that we use are powerful because they allow us to assess and to analyze our parallel algorithms in a way that helps us make certain assumptions. Like it is the formulation with respect to both work and resource utilization and also the time that is being used by the algorithm is a very powerful formulation. And on the other hand, this simple example shows that it's always important to question those models. Like the models make certain simplifying assumptions that can render certain algorithms completely useless when the hardware that we eventually implement this algorithm on doesn't have the exact same properties. So the basic takeaway here, the main takeaway here is that those models are very powerful and that they are the right models for us so that we can reason about our parallel algorithms. But we have to be aware of the assumptions that those models make, and we have to ascertain that those assumptions aren't too restrictive for what we want to achieve. So with that, I'm closing the session for today. Tomorrow we'll actually finish this first part of the lecture that is about performance of algorithms. We'll see another example for a parallel algorithm that we will discuss and that we will use to analyze work and time complexity a bit more. And then we will briefly recapitulate what we discussed in the last 5 or 6 sessions. And then we will finally start talking about rendering algorithms and about computer graphics and about the algorithms that essentially define the inner workings of a GPU. And I hope that you tune in tomorrow.